All right, my name is Matthew Ciolino. It's soft labels for rapid satellite object detection uh, from a company called PeopleTec. We're outside of Huntsville, Alabama in the United States, and I'll get started. So I'll start by introducing soft labels and get into our experiment, and I'll see results after that. All right, so this is kind of like the start of the soft label is the knowledge distillation task. Which is the ability to transfer knowledge into a smaller representation than the data itself. So this can be in the form of an embedding, or in the case of the picture you see here, you can just have the softmax layer output of one of the final layers of a classification network. So this hard label, you have 0, 1 dog, 0 car, and before selecting the highest probability value, it could look like this vector here. And one of the tasks that we can do with this is use a parent-teacher model to train a student on these soft labels here. So we can train a larger teacher and have the student train on the teacher's probability here, and then use a final classification layer with the actual true labels to train a much smaller model than the larger model. So this allows a smaller model to learn the teacher's target distribution, but we want to use a much simpler method for our purposes. So this is our introduction to soft labels. Think about scrolling through Google Earth or any other map-based viewer, and you just want to grab everything you can, all the objects from that image. That is kind of our approach to these soft labels. If you're looking for oil tankers, oil tanks, ships, planes, just about anything for satellite imagery, we take a pre-trained model. Let's say it's a YOLO v5 model trained on xView. We take that output target characteristics, so that's the width and height of the bounding box, and those are our soft labels for our purposes. So we take our inference output and we compile them into a data set of soft labels. And that's the basis for our soft labels. So why are we creating these data sets of soft labels that are not as good as a ground truth data set? So that gets us into our motivations and our requirements. So our clients are on the edge of current events, whether that wherever that is in the world, and they require rapid retraining on various target objects. So 1 week or month, it may be a certain type of plane or a certain type of car or anything like that. And so we want to, and they prefer models that do single target detection. And so we want to be able to rapidly create these data sets and retrain for single classes. And we need to do that in a limited time frame with the highest metric or fidelity possible. And so we wanted to see what the degradation in performance would be from a ground truth data set compared to using these not so accurate soft labels. See on the right here, this green box would be the true label, and the red box would be the soft label. So you can see that they're just slightly off pixels. They're still within the bounding box, the overlap, but they're just slightly off. So let's see kind of what our research goals are for this. So the above methods are all examples about how soft label can improve a model here. And so we're looking at how these soft labels affect performance and can they be used to categorize data sets automatically, hierarchically? And then what confidence value should we train the resulting model in based on the soft label threshold? And so let's just take a look at the experiment here. So we're using a subset of the xView dataset, a dataset released in 2018 with a $250,000 challenge by the NGA, National Geospatial Intelligence Agency. Their goal was to advance the frontier in computer vision. And so we took their dataset and we're using a YOLO v5 small model to run these experiments. And we use a common data set to see our results on a test evaluation metric of mean average precision and the other ones. So let's dive right in. All right, so here is our overview of the experiment. We're using a subset of the xView dataset. We subselect xView for moving objects. These are the objects of interest to us: vehicles, planes, ships. And that leaves us with around 35,000 images collected from parking lots, marine ports, airports, things where you would find the target objects. And then in addition, approximately 1/3 of the pictures are background, meaning that they didn't contain any instances of our target classes, but instead, via the guidance of the YOLO group, contribute to the null set. So overall, our data consists of about 37,000 instances of ships, 175,000 instances of cars, and 18,000 instances of planes. Okay, so we take this data. So this is the subset of xView movers, and we split into 3 different sets. We train 1, train 2, and test. And that's 40-40-20% split. And we train, let's say we do the train 1 on this 40% here, and then we generate the soft labels for the next 40%. And then we train a model on those soft labels, and then test on that unseen 20% that we found that we have in the beginning there. We do the same thing with the second training data set. So we train that. We then run inference on the other 40%, and we compare those against the ground truth performance with that last 20%. Okay, so hopefully that's straightforward. And then for each of these pre-trained models, we threshold the bounding box confidence to get a soft label data set at different confidence values. So if we threshold the trained model here at 50% threshold, only above 50% confidence value detections will be put into the soft label data set. Okay. So let's just show the results here. This is go into more, we have a graph later that will better explain, but here is, we saw the train set 1. We have the train set 1 soft label at 0.3% confidence, 30% confidence, train set 1 at 50% confidence. So while the soft label train models losses are both higher and lower than the ground truth model, we can derive some insight from the relative differences. You can see the differences here. Both the bounding box loss and the objectives loss, or objectiveness loss, are relatively consistent at an average difference of around 11.11%. But this is in stark contrast to the differences in classification loss, which vary around 45%. And since classification loss is the highest change, while still being the lowest component of loss, but it can be said that the unlabeled objects in the soft label training set, the ones that they miss, accounts for the loss in performance. So while the ground truth models perform best, you can see 0.76 mean average precision at 50% overlap, and 0.77 at 50%. The soft labels models consistently came within 6% difference for mean average precision and the F1 scores. And you can see the optimal confidence values for those F1 scores. And interestingly, the F1 score remains very consistent, with the optimal confidence value acting inversely to the threshold of which the soft label dataset was constructed. So you can see the F1 score of the 50% confidence is points. It's just called 0.7 at 0.318 confidence, while the one trained at 38% was about the same, but at a much higher confidence value. So when looking at these losses, this is the test set after the final epoch of training, but we can see a more interesting story if we dive into the per class metrics here. And that will give us a better look at what's going on. As shown, the majority, well, let's just explain this graph here. So we have 4 different metrics: precision, mean average precision, recall, and mean average precision at 95% overlap. We have the 3 classes: ship, car, and plane. And then we have just a clarifying legend here about which metric is which. So if we look at the mean average precision for planes in the bottom left here, you can see a drop from a train set 1, train set 1 soft label, and train set 1 soft label at 50%. Interestingly, for our most abundant class of cars, which has 175,000 instances, the largest number, we see a relatively consistent change in mean average precision, not decreasing for the first soft label at 30%, but staying around the same for 50% soft label, or 50% confidence soft label. And for train set 2, we can see a kind of similar result with the minority classes here performing worst over the different training metrics. Okay, so overall, the per class metrics dropped around 5%, each of these. And let's sort of discuss what we think could be a good application of this and other things. Okay. So while this drop is statistically significant in certain cases, i.e. like the planes, the benefits of soft labels outweigh this loss in performance by providing an avenue to get additional data in a low-cost method. So the xView team released how much it costs them to create their million object data set. And so in today's dollars, that's around $63 US per 1,000 labels for 3 people. So that's around $180,000 for these million objects in the xView data set. So if you think about what can we do to get that number down, the soft label is an avenue that we're showing can potentially be of great benefit. So we showed the loss of 6% between the ground truth and the soft labels, but however, this loss might be remedied by either balancing the data set, as you saw with the class, the car subclass metrics, didn't decrease that much, by either balancing the data set or increasing the amount of data for the lagging labels. We can kind of show a very insignificant drop in performance. So if your idea is to scroll across Google Earth and extract the objects you see into a data set, this is one of the most scalable methods to do that. So for example, let's say you want to fine tune a model on a specific region at a specific time of day. Getting ground truth information for that may be difficult. So these soft labels provide a different avenue to do that. So what are some of the issues? If we don't have a pre-trained model, there's no way to bootstrap from an initial model. In addition, if there is a change in the quality of images or um, the type of images you are taking, you could see a degradation in performance. In addition, if we are trying to translate our horizontal bounding boxes into different different labeling formats, like segmentation, rotated bounding boxes, or object tracking, or any number of other things, there is no way to easily switch between them via this method. That would require a whole nother model to be trained. So here are some of our applications that we thought would be interesting. Obviously, ground trained models. Let's say you have ground-based pictures of a plane on a runway. These wouldn't perform well on satellite images as expected. A model trained on a picture of airplanes from the ground level would never be able to predict one from a satellite image. So this gives the need for satellite image data sets to be created, of course. xView, Dota, and the other ones that we showed before are examples of these. However, with the large cost of these data sets, this method could be used to provide a way to get that at a cheaper cost. But as an extension to that, we can also extend those data sets via like hierarchical representations. So we have here examples of oil tank housing with blue roofs and white cars. So we can take a pre-trained model for buildings, oil tanks, cars, and extract the color of the roof. This is considered to be elite housing in some areas of Asia, and white cars in Turkmenistan could be another example of subtyping. So we could extract labels of cars, subtype them for color or oil tank inventory, and provide a very easy way to get a more detailed structure in a data set. So models can be trained exclusively on soft labels with less than a 6% drop in mean managed precision as compared to the ground truth on the same data set. We showed that with the xView data set with the YOLO v5 model. Regardless of the confidence threshold used to grade the soft labels, mean average precision and F1 scores remain within 1% of each other. And this suggests that while these soft labels are not overfitting to the training data, that they're not overfitting to the training data. And so these results kind of validate that rapid object detection data sets can be created with soft labels, and that soft labels can be used to train models with a high degree of accuracy. So in future work, we would like to use soft labels to improve the performance of the model on the test set by supplementing existing data instead of solely training on the soft labels. And many people have done research into that. Especially, we like to point out the rare planes model, or data set, which supplements real imagery with a substantial, much larger data set of synthetic imagery. We would also like to use soft labels from one generalized model that could be categorized to categorize any satellite image that you're looking at. And so during some of this work that during back 6 months ago when we were working on this, one of the methods that we saw come out was the open vocabulary object detection relevant model. This was trained on image text pairs, and it can be used to query an image with one or multiple text queries to search for and detect target objects in described in your text queries here. So if you see human face, rocket, it will try to pick out those objects from the image. Very cool model. And so obviously this is something, if you don't need your pre-trained model, you can use this one generalized model for everything. Let's see how this works. So to extend our paper on YOLO v5 and xView, we did a test on the Cocoa validation set with OWLIVIT, and then using OWLIVIT to create the data set and using YOLIV5 to compare metrics of when it was trained. So as shown here, using Cocoa validation set at 10% confidence and 25% confidence, we found a drop of 18% for OWLIVIT, 25% confidence, and a drop of 31% for OWLIVIT at 10% confidence.